Hello everyone, welcome back for a new video. Today I want to restart my explanation about TypeScript. I want to talk a little bit about conditional types. So today we are going to say what is a conditional type, and we're going to go all the way through the extends keyword, the infer keyword, and we're also going to have a look at the template literals with some examples that use the extends as well as the infer keyword. So let's start by a definition. What is a conditional type? A conditional type is a type that can allow us to describe the output of something, of a type, based on a condition. And this can be used to describe the relationship between inputs and outputs of a function. For example, let's imagine that we have an interface of type book, and here we have a cover which returns just a void, and then we have an interface of type myBook that extends book. So what we have a function that has ESBN and returns a number. So now we can define a type depending on this extends keyword that we're using here. So the type E is equal to myBook extends book. If so, then give me a number, otherwise return me a string. But we can also do other things. For example, E1, if for example a string extends book or myBook, then we return a number, otherwise a string. Here we're not doing anything really special. What we are trying to do is we are saying that this extends here, if what is on the left hand side of the extends can be assigned to the right hand side, then this condition becomes true, so is returned, otherwise this other one is returned. So in this case, what are we doing is we check if myBook extends book. If so, we return a number, otherwise we return a string. Now you might think this example is quite obvious, so why should I do something like this? So I'm going to give you a more real world example, which comes from a function I had to write a few weeks ago for work, in which we had a function that is going to produce a label, and the label is generated depending on a code number of the product or the name of the product, which is a string. So let's define those interfaces. So let's have an interface product code, in which case we have a code which is a number. Of course you can have other fields as well, and then we have another interface of type product name, where we actually have a name which is of type string. Now we declare some function, for example generate we give the code, which is a number, and in that case we return a product code. We declare a function. If we instead we give a name of type string, we're going to return a product name. And then we can do another function which can take a name or code of type number or string and return product name or a product code. Okay, so far so good. However, we have to declare 3 different overloads to define what is going to happen. So that when we give a number, it's going to return a product code. When it's of type name, it's going to return a product name. But what can we do? We can make this function take a generic type, and then checking such type, we can define which type to return. So we can have a new type, and we're gonna call it code or name of type t that extends number or string. Now, what we're gonna do, t extends number, so that this is our condition. If t extends number, then we're gonna return a product code. Otherwise, we're gonna return product name. So now we can have a function, generate product. This function is gonna take type t, extends number or string. Here takes an argument, which we call it name or code of type t, and then returns code or name depending on the type t. And here what we essentially have done, we can make this function work the exact same way without all of this declaration. It's actually going to return the correct type. So if I do const a equal generate product and we provide a string, we should return the product name. And in fact, a is of type product name. B, if you're going to provide with a number, is instead of type product code. Now let's imagine that we want to show both types at the same type. So we can have a const c, which is generate product. Then we put some random condition. So if mat random is higher than 0.3, then we return a string, otherwise a number. So C is of type product name or product code. All of this done just by defining it with this type, code or name. So all of this does is to say, well, check what is the type. So this is like a condition, it's a true-false condition. If the type t extends type number, so if t is a number, then return me product code, otherwise product name. Okay, so now that we saw this, let's see some other examples. When we have a conditional type, we may have constraints that can be coming from another type. A typical situation for this one a typical condition for this one is when we have a name or some parameter coming from an object. Let's imagine that we have an object that is const my object, which is name my name, and now we can access const a is equal to my object. Now we access it by name, and we know that a is of type string. What about if you want to make a generic type? So we're going to make a generic type so that we can do we can extract the name from such object. So we can do type get name. Let's do the get object name of type t is going to be t of name. However, TypeScript is complaining, is saying that name cannot be used to extend type t. Why is that? Well, because if t is, for example, a string, what is TypeScript supposed to do? This can actually throw an error at runtime. So what we can actually do to get object name and then we extract this variable t is to check if t extends an object which has a parameter name, and this name can be unknown. We don't need to know beforehand which type this is supposed to be. In such case, we can actually extract the name. So what we can do, we can say that get object type c is equal to get object name of an empty object. This is not working because we don't have a property name in it. So this is gonna throw an error, but if we have name Fred, then I'm gonna see that C is of type Fred. Now this example is pretty simple, but we can actually extend this to be used with interfaces. So if we have an interface and we call it my named interface, and we have a name of type string, and we have a type name type, which is gonna be get object name and of my named interface. So my named interface is gonna get passed to my object name, which is gonna get name and extract such string. So the type name type is gonna be of type string here. Now what we can do, we can also extend this get object name to do something even fancier than this. So let me comment this out, or actually I'm gonna make it as a second type. So we can do a type get object name 2, which takes a generic type t, and now if t extends name of type unknown, as we did before, then we can return the parameter t name. Otherwise, we return the type never. Because essentially what we're saying is, well, if the type t that we pass through has a name, they give me the name property. Otherwise, don't give me anything. So if we have an interface, let's call it person, and as a name of type string. Then we have another interface as an example. Call it video, since I'm making a video. And the video, instead of a name, as a title. What we are going to get, we can use a type person name. We can use get object name 2 and pass person. And we're gonna see that this one is extended type string. But then if we actually pass the video type, video name is equal to get object name 2 video, and this is gonna be a type never. What happens if we type it video name one, because it's the one we were doing before, get object name of video? TypeScript is actually going to complain because it's going to say, well, the type name is not present into the interface video. So this actually is a little bit more flexible as a type. What else can we do? We can extract types. Extracting types can allow us to flatten arrays, to extract the type from promise, from functions, etc. So let's have a look at a simple example in which, given a type t, if it's an array, we're going to extend such type. And let's have a look at some examples. Type output, let's call it out type of type t. We're gonna check if the type t extends any in the form of an array. So if it's an array of any, then we wanna know the type t of the number of the array, otherwise just give me the original type. So what this means? This means that if the type t is of type array of any kind, then give me the type that is given at any given location of such array. So if this is a string array, it's gonna be t is gonna be string. Let's have a look. So we can have a look of type get string. Actually, if this is of type string array, and then this is going to return a type t. However, if we have a number, and here we put simply a number, num is going to be of type number because this condition is false, so just the value is returned. Doing this, we can even extract a type from a certain location. For example, location type, t extends any, like before. We extract the type t at the first location, otherwise we return the original array. I forgot here to put t. So location type at 0 is equal to location type, or let's say 1, 2, 3. What it's going to do is going to take this array, it's going to take the element at the position 0 and take its type, which in this case is 1. So at t0 is 1. Again, this can also give a type where we don't need to give a particular type. So let's imagine that instead of number, the out type is gonna be of a mixed type. So if we have type mixed is equal to out type, and let's say it's an array of 1, 2, 3, hello, is of course not gonna be an array of type number, neither array of type string, but it's gonna be a union type, because it's gonna say, well, give me the different types that can appear on this array. So mixed is gonna be 3, 1, 2, hello. Okay, now that we've seen this, we can see some more advanced examples, and we can actually start to look at the infer keyword. So what we saw so far is that using conditional types, we do two things. We apply a constraint and we extract out of type. For this, we can do it with the infer keyword that makes it things much easier. Actually, let me take back my example. This is my out type t. I'm gonna remove everything else for keeping things simple. Now, if we have an out type t and we want to make this one type out type with infer, this is gonna be t extends an array, and then we can say infer I so So what we are doing here, we are saying out type with infer. So given a type t, if t extends an array of any kind, then give me the type that is inferred inside this array and return it. These two expressions are absolutely equivalent. So if I do out type of 1, we are going to see we get the exact same result. If we provide something that is not an array, we're going to see that we get a string in both cases. They work exactly the same, except the version with infer is slightly more readable. Now let's have a look at some more examples with the infer keyword. Let's write a type that can extract the return type from a function. So get return type, again we take a type t extends the arguments of the function, and then infer r is so return r, otherwise return never, because it means it's a function that doesn't return anything. So type a1 is equal to get return type of what? Of a function that takes no arguments and returns a number. So what this is doing is going to take the type r and return it. So r is going to be of type number. If we do another function where we give x as a string, then it returns a number, it's still a number. If this is an array, it's going to return an array of numbers, and so on and so forth. So we use the infer keyword to essentially tell TypeScript, give me the infer type that you get from this type. Now, one thing that I wanna connect back to the example I made at the very beginning, when I was doing that generate product code and product name. So if you remember, I did an interface product code with a code which was a number. Then I did an interface with a product name, which was a name, which was a string. And then I declared a bunch of functions. Let me find it, I'm gonna avoid typing. And now we need the get return type that I wrote just earlier. So when we have this function, and now we do this get return type of generate product, the infer is gonna go through this function, through the signatures, and it's gonna say, well, that T2 can be either product name or product code. But if I add a new line and I say that declare function generate product boolean returns a string. Now what is going to happen is that this t2 is going to be of type string, because the infer is going to read just the last one. So if this one is going to be here, you add it in the middle, t2, product name or product code. However, the reality is, now the new reality is that this one can also accept a boolean and can also return a string. And now it actually works. So that's important to keep in mind. Okay, now let's have another look at distributive types. We kind of already saw this one in a few examples before, but essentially what is happening is that when we apply a certain type, TypeScript is gonna distribute such type. So let's imagine that we have a type that converts to an array. It takes a generic type t, and if t extends anything, then return me t as an array. Otherwise, we have a type never, because of course, whatever type I give to it, it's gonna give it to me, or this condition is never met. So if I go type a1 equal to array, and this is gonna be string, a1 is gonna be an array of strings. But then what if I do, this can be a string or a number. Then this condition is gonna be, t can be a type string array or number array. So a1 becomes string array or number array. Let's say that we don't want this distributive approach. Then in TypeScript, the syntax is type to array non-distributive, given a type t is equal to t that extends any, if so returns t, otherwise never. And here goes the ternary operator. So type a1, a2 equal to array non-distributive of string or number. And now the type a2 can be a string or a number array, differently than the example we saw before. So let's have a look at some more examples, shall we? We can have a look at some funny examples that I was saying earlier. So for example, let's say we make a type flatten of type t. So when we flatten a type, it means that essentially we remove the array section. So if t extends array infer I, then return I, otherwise return the type t. So if we do flatten type t1, flatten 1 is gonna be just 1. But then if we have two arrays, t1 is gonna be an array of 1, because, well, we only need to go for the first half. Let's have a look at another example. Actually, this flatten is essentially the same thing that we have seen at the beginning when I was doing the out type. When I did the type out type of type t is equal t extends any, then we do t of number, otherwise we return t. This is exactly the same. Basically, the meaning of these two expressions is exactly the same. And in fact, we can actually think of it in the exact same way. Another way to type this one, type flatten to, t is t extends infer r, and again, this is another example of the same. These two expressions are essentially the same. In the first one, we say, well, if it's an array, then give me infer the type of the array. In this other case, we're basically saying, in the second example, we're saying is an array of any type, then give me the type of such array, where number essentially defines the type of the array, or the union type of the elements of the array. Here the same, infer the type R of such array. So these expressions are exactly the same. Another thing we can do, resolve promise of type t. So we take a promise, and now we infer type I. So what we do, we take a promise, and then we take the type of the promise, we infer the type of the promise, and then we return it. If it's not a promise, we just return the type t. Now, you might have heard about template literal types. And how about we do a couple of examples using the infer keyword and the extends keyword using template literal types. So we're going to make a utility type called invert. So we want to make an invert type where essentially if we have a binary invert, so if we have a 0, it's going to be converted into 1. If we have a 1, it's going to be converted into 0. So the type invert is going to be, we're going to take a type input I, and then a result that extends a string, which is initially empty. And now we have I extends, going to use our template literal. And what we're going to do, we're going to infer the head of the string, and then we're going to infer the tail of the string. Now, what happens if the string, essentially we go character by character, and if we're in the first portion of such string, I'm going to move to the next line, we can do invert the type t, otherwise using the template literal, we're going to do the return that has been done so far, concatenated with the head, and now we check if the head is equal to 1, then we return 0, otherwise we return 1. Finally, we return R. So let's have a look at this expression. We have an invert, binary invert, where given an input R, we want to produce an output R, which it's a string and is initially empty. Now the type I extends infer head and tail. So it's gonna take the first letter of such string, and this is gonna be the parameter h, and the rest, which is t. Now, if this is possible to do, if the letter is more than just one letter, I'm gonna invert the remaining, and with what I have right now, I'm gonna take r, and to r, I'm going to append 1. I'm gonna check if h, the current letter h, is 1, I'm gonna return 0, otherwise I'm gonna return 1, and when I'm done, which means when I doesn't extend anymore h or t, because remember that each time t decrements by one letter, then return the result r. So if I do type a equal to invert now we should see 0, 0, 0, 0, 1, 1, 0, 0, which is the invert of this parameter that we provided. Another example that we can have a look very quickly that might give you an idea of a more advanced use is, for example, make a type, which is a letter count, which takes a type input I, R, which again extends an array of strings, and initially it's empty. So now we do I extends, and we do exactly the same as before. We check infer h, and infer t. Now, what this is doing? This checks that the input that has been provided is made by more than one letter. If this is true, then I'm gonna call recursively this letter count with what? With the remaining of the tail, plus I'm going to have the head and r, which is my result so far. Otherwise, I simply return r length. So let's have a look. Letter count takes an input and makes a result that initially is an empty array with no elements, so length is 0. So if letter count of an empty string is 0. Now, if this can be split, so if it has one element, this string, I have h, which is the head, in this case 1, and t, which is nothing in this case. So what I'm gonna have an array made by the head, so it's the 1, followed by what was already there, which is nothing. And then at the second time, this is because h now is made by what was remaining from this string, which is nothing. This condition is not true anymore, therefore I'm gonna just return the length of a. So a is gonna simply be 1. Now let's say my name a is 8, because for each letter I'm gonna infer h, gonna infer t recursively, I'm gonna build up this array progressively, and I'm gonna count how many letters are in my name. There are many examples that you can find on the web using this. I hope this video was useful to you. If so, please leave a thumbs up, subscribe to the channel, or leave a comment. Thank you very much for watching so far. This was quite a lengthy video. See you next time. Bye bye.